Hello everyone. Uh, Hello everyone. Welcome. So this is a TA session for the NPTEL course on Introduction to Astrophysical Fluids, and this is the first week tutorial session. So we'll be having these sessions every week on Tuesdays from 7 to 9, same time, and we will discuss the uh, whatever has been taught for that particular week. So this is the first lecture on a series of lectures that are going to come. So I welcome you all to this tutorial session. Um, so I am the TA for this course, and so my name is Rohan. Uh, I am a PhD scholar at Indian Institute of Science, IISc Bangalore. Uh, I'm a PhD student, and I work on basically accretion systems, uh, especially around X-ray binaries or other mostly black hole systems. This could be collapsor systems, uh, or any other binary systems. So accretion is very closely related to um, astrophysical fluids, as we will also see in this lecture that these accretive systems are basically considered as a fluid or more like plasma, which are basically circling around the black hole or any compact object and forms an accretion disk as the matter falls into the black hole. Right. So yeah, so that's about me, and I'll be the TA for this course. So feel free to ask any questions uh, during the lecture, or you know whatever doubt you have from the uh, lectures given by the professor, or any problems related to this week you have. Feel free to stop me anytime and ask me questions. Right. So this week was basically an introductory week, and uh, right now, as far as I saw in the first 2 weeks, we won't be getting into the uh, exact fluids formalism. So, in the first 2 weeks, we'll be developing a formalism uh, which is more of a statistical mechanics kind of formalism, and from there we are going into a continuum formalism, which is the formalism of the fluids. So these 2 weeks would be how we go from a particle picture to a continuum picture. So we are very familiar with how particles work with classical mechanics, with quantum mechanics, right? So we'll extend the formalism of uh, how to go from that particle uh, picture to a continuum picture. So in a continuum, you have lots of particles, and instead of treating each particle as a separate uh, entity, you can treat them as a bunch or an ensemble of particles, and that's where we go into the fluid regime. So, in the first 2 weeks would be to develop that formalism of how we go from the particle picture to the the fluid picture or the continuum picture. So, yeah, right. So, let's start with the content for this week. So, basically, I will try to revise the major concepts that has been taught in the lectures, and then you can jump in and ask any questions that you might have related to that concept, or we will also do some problems along the way. We'll see what kind of problems could be asked and um, from these different concepts. Okay, so okay, let's start. Just give me a minute. Okay, so yeah, let's start with the content for this week now. Okay, so as I was saying, astrophysical fluids can be used in a lot of uh, astrophysical systems, and just to give you a motivation for this course about why you should take this course and how you can use the concepts learned in this course and in which systems can you apply them. So, fluids are basically a very important concept in uh, astrophysics, right? So, and they're used everywhere. So, for example, our sun in the solar system is basically a giant ball of uh, gas, right? You know that it has uh, hydrogen burning at the core, which releases this huge amount of energy. And, um, and, and for that matter, every star can be considered as a fluid, right? So all stellar systems are basically nothing but a ball of gas, right? So, so they are the very basic systems which you can consider them as fluid, and people model these stars using fluid equations, right? So, for example, we use this hydrostatic equations to describe these stars, and people do model uh, different kind of stars and using these hydrodynamic equations. So basically, the gravity is trying to, pull the star together, whereas you have this pressure term, which basically opposes the gravity. So the pressure force is balancing the gravity in a way, right? So this is a very crude way of explaining how to model a star, but mm, there could be uh, other features like magnetic fields and whatnot, right? So yeah, so now you can start off with a higher mass star with a bigger star, and then you can model how much pressure is needed to balance that star, and yeah, you can model different kinds of star like that, right? So yeah, so stellar systems or stars are one such system where astrophysical fluids are very important. Right. Another systems that are very important and uses fluids is that this picture if you see here on the right side uh, is a picture of a neutron star. Okay, so yeah, neutron stars are so basically what are neutron stars? So when a star evolves, right, and it burns all of its fuel, right, basically the hydrogen or helium, and then as it grows old, it doesn't have enough fuel to balance balance its force under gravity, right? So what happens is at the end of at the end of its life, the star collapses, and it collapses into a very dense fluid, right? Such that you know it's so dense that the neutrons in the star becomes degenerate, right? And that's where you call it a neutron star. Okay, so people try to model these neutron stars, and there's an active area of research that they believe that there could be, uh, I mean, you have to understand that these are very extreme systems, which have very high gravitational force, and if you put some matter into such high uh, pressure, uh, I mean, the neutrons become degenerate, right? And you could have different equations of state for such matter. So nobody knows what are exactly the equation of state of the matter within the star. So are they uh, do they follow normal, you know, equation state for matter, or for gluons, or do they contain quarks, or do they contain, they could contain any particle from the standard picture, right? So these are these extreme environments, and people try to model different equation of state for different neutron stars from the observations, right? Okay, so on the left bottom, you have these systems which are, as I was talking about, accretion. Right? So these are accreting systems. So you see this black hole at the center, right? And if there is any uh, object, for example, a star near this black hole, it drags in the matter from the star, right? So due to its tidal forces, it breaks the star apart, and it drags the matter into the star. And as the matter falls into it drags the matter into the black hole. And as the matter falls into the black hole, uh, it falls in a spiral path, which forms this disk like structure, which is called the accretion disk, similar to what might have seen in the movie Interstellar. Right? So this is how the matter falls in, and there are like various types of phenomena associated with these kind of systems. Uh, so, for example, uh, it's still an open question of the origin of these these are what are called jets, right? And people still, argue about what could be the possible origin of these jets from these accreting systems, right? So, yeah, and also there are various dynamics associated with these accreting matter. So, for example, some disks could be, very thin. I mean, geometrically thin, whereas disks could be, geometrically thick. So, what causes those? And yeah, so these are some important questions that are to be answered. And how fluids play a role in this system is that you model the whole matter that is falling into the mm, black hole, and you model them as fluids, right? Or plasma, so to say. And you solve the magnetohydrodynamic equations of how this matter or plasma falls into the black hole. And that's how you get this uh, systems, right? So, yeah. Also, on the right bottom is a picture of interstellar medium. So, interstellar medium is the medium between the stars, right? And so they are mostly composed of gases, right? So they are modeled as gases. So you see this gases, and wherever these gases become dense, they form these nebula, which are the star forming regions, right? So, depending on the density of the gases and the temperature, certainly in some dense regions of this nebula, we could have uh, formation of stars as well. So these systems are also modeled as fluids. Okay, so yeah, so these are some of the systems only which uses astrophysical fluids. And these are all very active areas of research, and people still don't know many phenomena associated with these systems. Okay, so moving on. Okay, now as I was saying, these 2 weeks would be how we get from a particle picture to the continuum picture. And when we say particles, we talk about classical mechanics or quantum mechanics, right? So what does quantum mechanics tell us? Like, uh, I mean, and what does classical mechanics tell us? At which regime does is exactly we go from classical to quantum? How do we decide that? How do we know that whether a particle will follow the laws of classical mechanics, or let's say Newton's laws, or in which case the particle will follow the laws of quantum mechanics, or let's say um, Schrodinger equation, right? So I think you're all familiar with this uh, something called de Broglie wavelength, right? So this is a high school concept which is defined as this Planck's constant divided by the momentum, right? So h by p, right? Now, you also know that the kinetic energy of a thermal, uh, well, let's say, uh, particle is 3 by 2 kT, right? And if you just, replace the kinetic energy over here with 3 by 2 kT, you get this. So this is the relation between the de Broglie wavelength and the temperature, right? So why are we talking about these de Broglie wavelength, right? So, right. So now it turns out that, well, all particles can be treated as waves. right? So that is the basic concept of de Broglie wavelength. And this lambda gives us the wavelength of that particular particle. And it turns out that for most classical particles, so for example, let's say uh, for a person, right, who weighs, let's say, uh, 60 kgs, have some energy, and it turns out that if you calculate the de Broglie wavelength of that person, it turns out to be very, very low, low enough to be considered negligible. So all classical particles have negligible de Broglie wavelength, right? Whereas quantum particles have very high de Broglie wavelength, right? So that's how you distinguish whether a particle will follow the laws of quantum mechanics or classical mechanics. So you check the de Broglie wavelength, and if the de Broglie wavelength is comparable or larger than the interparticle distance between the two particles, then we say that okay, the particle will behave in a quantum mechanical way. Okay, otherwise it will behave in a classical way. So let's say you have a container of gas, and you have this gas molecules within that container. Okay, so now you have a certain density. You know the density of the gas inside the container, and from that density you will know what will be the interparticle distance, right? So let's say n is the number density, that is the number of particles per unit volume. So total number of particles divided by the volume. So that is given by small n. Okay. So now you have these n particles, so capital N particles within the volume capital V. So the number density of the particles is small n equals to capital N by capital V. Now, what should be the interparticle distance between any two particles? So it should be given by 1 by n whole to the power of 1/3, right? So now you have to check if the de Broglie wavelength of the particle is comparable to the interparticle distance or even greater than the interparticle distance, then the particle will behave quantum mechanically. Otherwise, the particle will behave classically. So you just equate this lambda to be uh, equal to 1 by n whole to the 1/3. And if lambda is much, much less than 1 by n whole to the 1/3, it will be, classical. And if lambda is much, much greater, then it will be quantum mechanical, right? So by doing that, you will arrive at this equation, right? So now what does this equation tells us? So if the temperature is very high, right? If the temperature is very high, then what will happen? So this term will become greater than this term. So then it will behave classically. So this is the condition for it to behave quantum mechanically. Okay. So on the other hand, also, if the number density becomes very high, then it will again behave quantum mechanically, right? If the number density becomes very low, then it will behave classically. Okay, so this is the condition for the particle to behave quantum mechanically. Okay, right. Now we'll just do a simple question just to get this idea. So we have these. Uh, so air is mainly dominated by nitrogen molecules at room temperature at around 1 atmosphere. So you know the pressure, temperature. So you know the temperature, and now the question is: are these molecules close enough together that their quantum wave functions overlap, forcing us to abandon classical physics and use quantum statistics. So, as I was saying, if the de Broglie wavelength is large enough, so it's such that you know the waves overlap, quantum wave functions overlap, then it will behave according to quantum statistics, right? So, is this true for air molecules? So now we have seen that it has to be very dense to follow quantum statistics. It has to be very low temperature, very cold to follow quantum statistics. Now, are air molecules dense enough or are they cold enough? That's the question we are asking. Okay. So, how to solve this? You know the temperature, right? Now, so these are the Planck's constants. So the physical constants, Planck's constant, Boltzmann constant, and the nitrogen mass, right? So now we also know the temperature, which is given, the pressure we know. Now, using ideal gas law, we can calculate the value of n, right, which is the number density, like this. So this turns out to be something like this. Okay. So now we know the number density, we know the temperature. Okay. And we also know the value of these constants, right? So the next step would be just to calculate the left hand side, right? So this turns out to be 10 to the minus 22, right? And the right hand side, which is a constant value, this turns out to be of the order of 10 to the minus 62. So if you see that the left hand side is very, very bigger than the right hand side. So it doesn't follow that condition. So it doesn't follow quantum statistics. So that's why we can fairly treat the air molecules as classical particles. Right? So this is just an example. Now, you can think of many such examples, right? And the main concept that we try to learn from this calculation is that when to treat particles quantum mechanically and when to treat them classically, right? Okay. So yeah, I guess this is an important condition that you can check, and I guess many questions can be asked on this. Okay, moving on to the next slide. Okay, so the next topic that we're going to do is study what are called phase space, right? And from there, we will see how we see this very important theorem, which is called Liouville's theorem, and we'll see its implications as well. Okay, so okay, so now, but before understanding Liouville's theorem, we have to understand what is phase space, right? So let's look at phase space from an example. Okay, so for example, you have this system, which is basically a spring mass system. Okay? So you have this mass which is moving in time, and you can see, uh, you know, you can track its position in time. So that's the real space. So the real space is you have the position versus time, or x versus t. You can plot that, right? And you can track the position of the particle at every instant of time. And from there, you can calculate the velocity or acceleration of the particle by taking double derivative, or you can understand what the particle is doing in real space. Now, what is phase space, right? So, phase space is a plot between the position and velocity. Instead of position and time, you plot position and velocity. So, if you look at this box, you see what is the position of this box at this time, right? So this green dot, and what is the velocity? So if you see the box at towards the end, the velocity becomes zero, right? So when it goes to the end, like this point, its velocity is zero, and this is the other end. When it goes to the other end, again the velocity is zero, right? And when it's in the middle, this velocity is maximum, right? So that's how. And therefore, in the phase space, this object follows a very beautiful circular path, right? And from there, you can identify a lot of properties of the object, right? Which we'll see now. Okay. Now, this is the phase space for one particle, one object. Okay. What if we have many objects? Let's say we have n objects or n particles in a gas, right? So you have a system, you have a container full of gas particles, and you have n number of particles, gas particles in that box. Now, for each particle, there will be this phase space for each particle, right? So we'll have n number of phase spaces, right? Now, what should we do? Should we like plot n number of phase spaces? How should we represent this, right? So turns out that we can represent this system of particles in two ways. One is this gamma space, another is this mu space. So what is gamma space? So one way you can do is that you have these n particles, and each particle will have uh, the dimension of the phase space for each of this particle will be 6 dimensions. So where does this 6 comes from? So you have three position directions, x, y, z, and you have three velocity directions, vx, vy, vz, and three directions, right? So in this plot, we are just showing movement in one direction only. It can only move in the x direction, let's say. But when we have a realistic system, it can move in any direction, x, y, z. Also, it can have velocities in any direction, vx, vy, vz. Right, will be the three components. So you will basically have six and uh, dimensions, right? So you cannot plot a six and dimension plot, obviously, but if you can imagine, right, that you have a six and dimension uh, uh, space, okay, and in that space, if you have a point, right, that point can be represented by 6n values. So, for example, in a 2D plot, let's say this position and velocity plot, any point can be represented by the dimension x and y, x component and y component. So, x component with the position, sorry, x component with the velocity, y component with the position, right? Similarly, in a 6n dimension plot, you can represent one point with 6n values, and those 6n values are the 6n 3n values of position and 3n values of velocity, okay, of the n uh, particles, right? So that is how we represent a state of the system in gamma space. So it is represented by a single point, okay? And probability density in gamma space is represented by this rho, right? And it is a function of QIN, which are the position, PIN, which are the momentum or the velocity, you can say. This will have n terms for n particles, and i's are basically the x, y, z, these three directions, okay, and t time. Okay, now what about mu space? So mu space, the dimension of mu space is only 6. Now, how do you represent these n points with only 6 dimensions? So earlier in gamma space, we required 6n points, 6n, sorry, values, right? So here also, we will have 6n values. Obviously, we'll have the 3n position values and 3n uh, momentum values as well, right? So, in order to have n points or n particles, in order to represent the n particles in this mu space, we will require n points, 1 point for each particle. So, we'll know the position of one particle and the velocity of one particle at some time, and we'll represent it by 1 point. Okay. Now, we'll have similarly uh, n points for n particles, right? And for each point, it is a 6T space, 3 position values and 3 velocity or momentum values, right? So it will basically be Fn, n number of particles, each represented by Qi, Pi, T. Qi will have 3 components, Qx, Qy, Qz, and Pi will be Px, Py, Pz, right? Okay. Now, yeah. So how is this phase space used in Liouville's theorem? So Liouville's theorem states that any volume in phase space will remain constant as it evolves, even though its shape may change. So this is a very powerful theorem, and we will see how we can obtain the equations of fluid with the help of this theorem, right? So now, what it means that if my particles occupy these uh, volume in the phase space, right? At some later time, when it evolves, it could occupy a different patch, but the total volume of both the patches will remain the same, right? And to mathematically represent this Liouville's theorem is to say that the total derivative of this probability density should be zero, right? So now probability density is a function of Q, P, and T. So you have to take the partial derivative with respect to T, and then you have to take the partial derivative with respect to Q, and then multiply by Q dot, then partial derivative of rho with respect to P and multiply by P dot. So this simple chain rule, right? And this total thing should be equal to 0. So that is what is the statement of Liouville's theorem. Okay, right. Okay. Okay. So before we move on, let's take a quick break and uh, we'll continue with the rest after the break. Okay. Okay. So, any questions so far on up to whatever has been covered? Okay. Okay. Now, okay. So this is another concept that we are gonna need very frequently, uh, and this is a very fundamental thing that is used everywhere in any system in which you have fluids. So I guess you might have already heard about it in a different context, and this is a very fundamental phenomenon. So this is something called the equation of continuity, and which states that anything that is coming into a volume. Uh, so basically, what we're trying to see is we are trying to see that within this box, within this cube, uh, what is the rate of change of fluid density within this box, or let's say any other quantity. So in this case, we're trying to see what is del rho del t within this box. So del rho del t, what is the change in the density of the fluid, will depend on how much flux is coming in and how much flux is going out of this box, right? So if you see, right? So at this point, at the center of box, we see the flux is rho ux, rho uy, and rho uz in the three directions. Now, this edge of the box is at, so if you consider this is, uh, well, this is the x-axis, y-axis, z-axis. So this is edge of the box is at, so if you consider this to be 0, so this will be at 0 plus delta y by 2 distance, right, from the center. This edge of the box will similarly at minus delta y by 2 from the center. Okay. So now, if you do a Taylor expansion of this, of the flux that is uh, coming out from this face, right? So the flux is rho uy at this one, at the center. So now if you just do the Taylor expansion of rho uy at uh, delta y by 2, you will get something like this: rho uy plus del rho uy del y times delta y by 2, and del x del z is basically the area of this face, right? So now what you're trying to see is how much of flux is coming out of this face. So flux, is uh, you know just the quantity dot with the area. So if q is the quantity, q dot dA. So dA is given by this delta x delta z, and the flux, the quantity, is basically rho times cy plus del rho uy del y by 2. And similarly, at this face, what is the flux going in is given by a minus, just because this is at minus delta y by 2. Similarly, you can calculate the fluxes at the other faces, right? And now what you will do is you will see that del rho del t is basically equal to the fluxes coming out of all the phases, right? So del rho del t, and so if you just so this is going out, this is coming in. So this will be this minus this. So if you do this minus this, the only term that survives is del rho uy del y, right? Times del x del y del z. So del x del y del z will be associated with all the terms, and you will have these extra terms del rho uy del y, and del rho ux del x, and del rho uz del z. So this is how you write the continuity equation, right? And similarly, in compact form, this can be written as del rho del t plus del dot rho v equals to 0. Okay. So this is another way to derive the continuity equation. Okay. And this will be very important in fluids. Okay. So let's move on. Okay. So now we know we have studied the this will, I think, continuity equation will be covered later on as well in the lecture. Uh, and we'll derive continuity equation from uh, the Boltzmann equation in week 2. So Boltzmann equation is what we're going to study next. But I just wanted to give you a flavor of what this equation of continuity talks about, because this is a very important equation in fluids. So, and not only in fluids, it is also, you can draw analogy in electrodynamics of, continuity of uh, charges or currents. So basically, it just talks about that, you cannot have accumulation of something within um, in a finite volume, right? So if there is some matter coming in and going out, and the rate of change of some quantity should be equal to uh, the matter coming in and minus matter coming out, right? So that's how the rate of change of matter within that volume would vary with time, right? Okay. Now, right. So we'll do Boltzmann equation, and this is a very important equation in statistical mechanics. And you will later see that using this equation, we can derive the fluid equations in continuum, right? So this is going to be the equation which is going to help us to move on from this particle regime to the continuum regime. Okay. So as I said that so we are going back to the phase space now, right? So if you remember, in the phase space we have this uh, ensemble of particles, right, which were represented in the phase space. And if you remember that we used to represent the uh, density of the phase space, or the ensemble density, as some function of position, momentum, and time. Right? Now, let's see that let's say that f is the uh, f is that function, which is a position, which is a function of uh, position, momentum, and time. Okay. Now we'll have three position x, y, and z, and you'll have momentum px, py, pz, right, and time as well. So if you just do chain rule and check the difference, check the df, you'll get something like this, right? And again, you can decompose this as this thing, right? So del f dot dr. So this is this part, right, in vector form. And again, this part in vector form would be something like this. Now, here what they have done is that just they have, you know, uh, changed dr to p by m dt, right? Because we are more familiar with uh, instead of r, uh, we are using p and m. So like p by m is just so p is momentum, right? Right, is mv, right? And so mm cancels and vdt is dr, right? That's how you get it. And similarly here, dp is basically fdt coming from Newton's second law. So f is dp dt, and you have dp as fdt, right? So right now from Liouville's equation, we saw that uh, that del rho del t should be equals to 0, right? So similarly here, if we do df dt, right? So if you just take this dt and uh, tend it to 0, so you will have this thing only. You have del f del t plus gradient of f dot p by m. So p by m is p, and again f dot you know del f del p. So this is a gradient with respect to p. So one thing you have to note here. So this is a gradient with respect to p, and this is a gradient with respect to the spatial coordinates r. Okay, so that's the difference here. So this should be equals to 0. Okay. Now there is one catch here. So in Liouville's theorem, we assume that there is no interaction between the particles, right? But what if we have some interaction with the particles, and the particles are colliding with each other, and there is scattering involved. So what will happen is that the volume might not be conserved, right? So the particle might go out of the volume by scattering with each other, and so on, right? So instead of 0, in that case, if there are collisions and there are interactions within the particles, we'll have some scattering term, del f del t scattering, uh, and not 0. Okay. So this equation is called the Boltzmann equation, right? And for most cases, for collisionless cases, we can assume that this is equals to 0. But if there are collisions present, we have to say that, okay, this is not 0 and this will be del f del t. So in the next slide, we will calculate, or will motivate how to calculate this scattering factor or this collisional factor, right? And why is that important? Okay. So before that, we have to understand in which regime are these collisional factors or scattering factors important, right? And in which regime we can just fairly assume that they are negligible and they can be taken to be close to 0, right? So there are two ways you can visualize that, right? So for example, one way, okay, so to explain this, let me go to my notepad. See, okay, so this is the first condition, pi n e cube much less than 1. So yeah, so what does this mean, right? Let's talk about this a little bit. Okay, okay. So so again, let's assume that you have a box. Mm, it is showing a lag. Check. Okay. Yeah, yes. So now let's assume that you have a box of gas with many particles like this. Okay. And again, as I said, the density of particles is n, which is number of particles divided by the volume. So this is called number density. Okay. Right. Now, okay. And also you are given the size of the particles. Let's say it's given by A. And you can assume that, so A is the radius of the particle, radius of each particle. And you can assume the particles to be spherical, and therefore the volume of each particle should be 4 by 3 pi a cube. Right? Now you can, like, from an intuition, you can see that if the particles are very small, right? The 4 by 3 pi a cube is very, very small compared to the inverse of the number density, right? So what does 1 by n give you, right? So 1 by n will be equivalent to saying that it is b by n. So from the definition here, right? So if you see here, 1 by n should be equivalent to b by n. So it will give you the volume occupied by each particle, right? Now, if the volume of the particle, so like if the volume, you know, of the particle is much, much less than the volume available for it, you know, you can safely say that, okay, they are not colliding with each other, right? So this is the condition for, you know, for particles to not collide with each other, right? Whereas if you want particles to collide with each other, then this should be comparable. So pi and a cube should be much, much greater than 1 if you want the, you know, particles to collide with each other. So this is much, much less than 1. So that means, you know, this is a collision-less regime actually. It's the collision-less regime. Right. Now, so this is the first way to go about it, right? So there is another way also to look at it. So from there we'll get another condition. So this is the condition for mean free path. Okay. So let me see. Okay. So we have some space over here. Okay. So let's just motivate the idea first from here. So let's say you have this volume, this cylinder of, you know, of gas molecules, right? And these dots are basically the centers of uh, all the molecules that you have within this cylinder, right? Now you consider that, okay, so there is another molecule which is going through this gas of molecules, and you want to understand that, uh, you know, how many collisions will this particle go through, right? So let's say that this particle has a diameter d. So sorry, let's say the cylinder has a diameter d, and this particle has, you see this particle in red, right? So this is the particle which has let's say, diameter of d by 2. Now, if it has a diameter d by 2, so then it's going to collide with all the particles whose centers are within this cylinder, right? So as I said, these dots are basically the centers of the rest of the particles, and this is going to collide with all these particles as it goes through this cylinder, right? Now, okay. Now the length of the cylinder will be the v into t. V is the velocity of this molecule, and the time taken for it to cross the cylinder is t. And the area of the cylinder would be pi d square. Volume of the cylinder will be pi d square of vt. Now there is another concept that we want to introduce here is that mean free path. So mean free path is the average distance a particle travels between collision. So for example, the length of the path taken by this particle till it collides with another particle, right? So that length is basically the mean free path, actually the average of that length, right? So if it has n collisions and you calculate the path, the length of the path that the particle traverses in between each of those collisions and you average them. So that is basically a mean free path. Okay. So now, well, how to understand whether the particle is in a collisional or collisionless regime from mean free path? So we're gonna see that, but before that, let's see how can we calculate mean free path from this, uh, from this picture. Okay. So again, let's go back to the notebook, sorry, whiteboard, and let me draw this picture in. Let me see. So this is the particle we have, and this is the cylinder. Okay? And it's gonna collide with all the particles whose centers are within this sphere, right? And as I said, this distance is Vt. The volume of the cylinder is pi d square Vt. Okay? And the number density of the particles is given by n, okay? Which is, as I said, is n by v. Okay? So let's first try to see number of collisions this molecule will go through as it goes through the cylinder. Okay, so that will be given by pi d square Vtn, right? N is the number density, pi d square Vt is the volume, right? So this will be the number of collisions this particle will go through, or in other words, the n, the value of number of particles within this cylinder, right? Because it will collide with all the particles within the cylinder. Okay. Now we want to understand what is the mean free path, right? So the total length is Vt, and number of collisions is this thing. Okay. So the mean free path, MFP, also denoted by lambda, is basically the length divided by the number of collisions, right? Okay. So this is the total length, and if it, let's say, if it has 5 collisions in traversing this length, so that means the between each collision, the total length divided by the 5, the number of collisions it will go through. So that will be the mean free path. Okay. So this will turn out to be 1 by pi d square n. Okay. Now, if you see in the slide, this is almost 1 by pi d square, n by v is n, small n, and there is a root 2 factor. So where does that root 2 factor comes from? So it just comes from the fact that these particles are also not stationary. Okay? So these particles are also moving. Okay? So therefore, in the whole calculation, we have assumed that these particles are stationary, and but we are only considering the velocity of this molecule. Okay? And if we consider that the particle it's colliding with are also moving, so you have to consider the relative velocity between the particles, right? And if we consider the velocity of those particles also to be v, so the relative velocity, so you will get a root over of v square plus v square, which will be root 2v, right? So if you do a vector uh, addition of the velocities, and you'll get that root 2 factor ahead of this. Okay, so that's how you get the root 2 term over there. Okay, but we saw that the mean free path is given by this. Now the question is how to understand whether the system will be collisional or collisionless from the mean free path concept. Okay. So now you can understand that well, if you have a very dense system, right? What would you expect? You'll expect the mean free path to be very low, right? Okay. Whereas if you have a very rare system, the particle can move on freely for very long distances without any collision, right? So the mean free path in those systems will be very high. Okay. So that's how you can understand whether depending on the mean free path, uh, that how whether the system will be collisional or collisionless. Okay. So okay, these are the two ways from which we can see if the system is collisional or collisionless. Okay. Now, okay, so this is the last concept that we are going to do. Now we already saw the derivation of the Boltzmann equation, right? Okay. And as we said that we are going to explicitly calculate what is going to be the collisional term, right? And because for the left hand side uh, we are clear, given the system, you can calculate the left hand side, but the right hand side do not have an analytical expression yet. But that's we are going to see how to calculate the right hand side of this equation. The right hand side, as we saw, is called the collisional term, and here's how we are gonna motivate it. Okay. So, for example, what we are gonna see here is that, as we said, that now the particles are colliding with each other, right? And if you consider a volume, you know, uh, you consider a volume, and within that you have, let's say, n particles, and let's say you have uh, another set of particles which have density n1, let's say small n1, so n and n1. So the first set are moving with velocity u, second set are moving with velocity u1, and they collide, right? And if they collide, then the momentum of the particle could change, right? So the particle which has u will, let's say, after collision, will have velocity u dash, and u1 will have velocity u1 dash, right? So we want to understand what is the change in the number of particles who are changing their uh, phase space basically. So initially they are within a certain volume of phase space. After collision, they are going out of the phase space, right? And similarly, there will be some particles which are coming into that phase space from outside, right? So you have to consider those particles as well. So which will let us see. So C out is what is represented by the number of particles which are going out of that phase space, right? Whereas C in will be the particles which are coming into the phase space, right? So yeah, but let's start from here again. Okay. So delta NC is the number of particles which are basically leaving the phase space, right? And that is proportional to uh, number of particles present in N1 and Q minus U1 and sigma omega, which is basically the cross section of collision, sigma omega d omega. Okay. Okay. So now, as we know that N is F d3U, right? So if you see what is the total number of particles? So total number of particles is the uh, F times the uh, integrated over all possible velocities, right? So that will give you the total number of particles, right? Similarly, N1 would be all the particles with velocity U1 integrated over all velocities of uh, integrated over U1, right? And then U minus U1 sigma omega d omega, right? So now we want to see, okay, so we want to see the number of collisions per unit time within the phase volume d3U, okay? So yeah, so we want to integrate over u1 and omega, right? So this will, if you integrate over this, you'll get the number of collisions per unit time within this phase volume, right? Now, as I said, there will be some particles which will be, you know, uh, moving out of the phase volume, right? So this will be, so if you just integrate over d3x as well, right? So if you see going from here to here, you're just integrating over d3x as well. Well, not integrating, you're just considering the phase volume d3x. Okay. So, so these are, as I said, are the particles which have initial velocity u1, u1, and finally they have velocity u dash and u1 dash. Okay. And C in, on the other hand, are the particles which has initial velocities u dash and u1 dash, and final velocities u and u1. Okay. So yeah, so that's it. And the collision integral would be basically the number of uh, you know the number of collisions that you get from so there are some particles which are going out of the phase volume, and there are some particles which are going in. So you have to subtract those which are going out, and you have to add those which are coming in. And if you do this, if you do C in minus C out, and if you use these conditions, so u minus u1 equals to u prime minus u1 prime. So this is just the conditions coming from conservation of uh, momentum and energy. So this is the condition that is coming from Liouville's theorem, which says that the phase volume remains constant. And this is the condition coming from symmetry arguments that there should not be any difference in cross section uh, for the forward process and for the reverse process. Okay, so if you use this and if you do C in minus C out, so you'll get to this simple term, which is d3u1 u minus u1 sigma omega d omega f prime f1 prime minus f f1. Okay, so yeah, so f is this thing, this is f1, this is f prime, this is f1 prime. Okay, so this is the collisional term that we obtain finally from the uh, from this analysis. Okay, right. Any questions so far? So the final Boltzmann equation would be this thing, whereas the right hand side will be given by this term, right? And this term will be zero for collisionless systems, will be, and it will be non-zero only for collisional systems. Okay. So yeah, I guess so just a quick recap of what we did today. So okay, as we are talking about the applications of astrophysical fluids in different systems. So I mean, starting from stars to galaxies to black holes, accreting, and all kinds of exotic astrophysical systems can be explained with the help of fluids, right? Fluids are uh, everywhere in astrophysics, you know. And then we uh, started about how we can go from a particle picture to a fluid picture or continuum picture. So we started with the de Broglie wavelength, right? Which is um, and it should be much less than the interparticle distance in order to um, have the system behave according to classical laws. Whereas if the de Broglie wavelength is comparable to the interparticle distance, then it should be, you know, it, it should behave according to quantum mechanics. Then we did a quick, example where we showed uh, how we can have, like, for a simple system, our air molecules to be treated, you know, classically or quantum mechanically, right? So we just check this condition, and, and from this condition, we have to see that if n is high, right, n is very high, then this will more. I mean, the system has to be very dense in order to behave uh, classically, sorry, quantum mechanically, right? So if n is very high, so this condition is going to be satisfied. And on the other hand, if t is very low, again, this condition will be satisfied. So you have to see both, whether t is low or n is high. mm, and if this condition gets satisfied, then the system behaves quantum mechanically. Otherwise, it will behave classically. And we did this example, and yeah. Then we went on and talked about phase spaces and its relation to real space. And we talked about gamma and mu space and how they are different and how we can represent uh, an ensemble of particles in this phase space. Also, we studied Liouville's theorem and an important uh, consequence of Liouville's theorem. Uh, so, right now, then we moved on to equation of continuity, and we saw how we can derive this equation, right, by just taking this uh, volume of fluid and checking out uh, the flux of uh, matter coming in and out of the fluid, which would be equal to the change in the density of the fluid, right? Then we moved on to Boltzmann equation and how we can derive it from Liouville's theorem. So, according to Liouville's theorem, the derivative of probability density should be zero. And if we consider this probability density as a function of uh, position, momentum, and time, we can represent it in this way, uh, just using chain rule, and this should be equals to 0. But for collisional systems, this should be equal to the del F del T of the collisional term. Right? So now we saw how we can define a collisional system and how is it different from a collisionless system. So for a collisionless system, the interparticle distance has to be uh, very high compared to the uh, size of the particle, right? And in other way, we can also see it from the mean free path. If the mean free path is very high, we can call it collisionless. And we just calculated, we just saw how to calculate this mean free path lambda, right? Now we calculate the collisional term in Boltzmann equation, and we just argued that uh, so in presence of collisions, there will be particles going out of the phase space, and similarly there will be particles coming in out the into the phase space from outside, and the change in the probability density function due to the particle going out and coming in is just given by the C in minus C out, which we calculate like this. Okay, and C out is the number of collisions uh, that is kicking the particle out of the phase space, and seen is the number of collisions that is bringing the particle into the phase space from outside. So del F del T is seen minus C out, and this is given by this simple form. And so basically, if you have some two particles which are colliding, U1, U1, whose final uh, velocities after collision would be U prime and U1 prime. And similarly, if you have particles which have U prime and U1 prime, uh, and after collision they have velocities U and U1 prime. So, sorry, U and U1. So, uh, that's how you calculate C in minus C out, and you get this equation, right? So, this is all. Now, for reference, you can refer to this book. So, this is a very standard book for statistical mechanics. So, yeah. So this is how it looks. I also have a copy of this book. And so for the purpose of this course, you don't have to go through the entire book. So all the materials that are covered in week one uh, is present in chapter 3 of this book. Right. So we'll just do chapter 3, 4, and 5. Yeah. So these three chapters would be enough for this course. So even I think you can, yeah. So I think this week one will be chapter 3, and week 2 it's mostly content from chapter 4 and 5, right? So you can go through this book, and this has very clear explanation of all these things, right? Okay. So this book only contains the uh, content from the first 2 weeks of this course. So later on, we will refer to different book. Okay. This doesn't have fluid. Uh, like this is not a book for fluids. So this is a statistical mechanics book, and uh, it just talks about Boltzmann equation, and it just introduces how we can uh, derive the fluid equations from the Boltzmann equation, right? Just from a uh, statistical to continuum transition point of view. So, yeah. Okay. Any other questions? So we'll have this meeting every Tuesday, and we'll have uh, sessions on Gmeet as well as on YouTube, and the YouTube lectures will be recorded and will be provided to you. Okay, and you can also join. Well, you can join on either Gmeet or on YouTube Live as well. Your choice. But yeah, if you have to ask questions, uh, I'd urge you to join on uh, Gmeet. But you can also later, uh, look at the YouTube videos or leave a comment asking questions if you have any, or you can also ask on Gmeet. Yeah. So if you don't have anything, then I guess we can close the call and we can meet next Tuesday. Okay. Yeah. So see you next Tuesday.